Welcome to the 9th section of the seminar on EDP and the applied mathematics. Today, we will have the participation of two excellent researchers. First, Serena Dipierro from University of the Western Australia. And the second, Ovidio Rubio Mercedes, de la Universidad de Trujillo, Peru. To introduce the professora Serena, eu quero de professor Diego. Please, Diego, introduce the speaker.
Okay, thank you very much, Professor Mauro. For us, it's a great honor to receive Professor Serena Dipierro from University of Western Australia. Professor Dipierro is an Italian mathematician. She's involved in many research topics like PDEs, regularity of solutions, no-local operator, free boundary problem, and some applications in many fields. She received her PhD in 2012 in the CISA in Trieste. And today she's going to talk about no-local capillarity theory. So, Professor Serena, welcome, and start. The word is yours.
Yeah, thank you very much. Thank Diego for the introduction, and thanks to all the organizers for inviting me. It's really a big honor for me to speak in this series of seminars. Okay, so I will talk about some kind of recent results on this non-local capillarity theory. And so let me first describe a bit what classical capillarity theory is. So this is somehow related to more general phenomena that are due to surface tension and that are topical in virtually basically many branches of science, so physics, material sciences, biology, chemistry, and so on. And so the idea is that surface tension is in general a complex phenomenon to describe, and it is the macroscopic outcome of a bunch of microscopic phenomena that are basically due to molecule interactions. So for instance, cohesion, which is the interaction between molecules of the same substance, or adhesion, where you have molecules of different types that interact. So in general, you may also have long-range interactions between molecules, and basically the surface tension, what we call surface tension, is the final outcome of all these forces, all these interactions between molecules. And so the classical theory essentially produces a model of surface tension, so sees the surface tension as a local average of these forces between molecules, which in principle may possess long-range contributions. And so, for instance, I will focus on capillarity theory. Specifically, I will have a container, omega, which in the mathematical setting will be an open and reasonably smooth set. And then I want to describe the formation of droplets in the container. So I'm talking about like small, for instance, drop of water, so something like that. And the idea is that so you have this droplet in this container, and you want to understand the shape of the droplet and where it sits in the container. And so the idea is that basically you minimize a perimeter-like energy function of this type. So the droplet will be represented by a set E, which is contained in omega. And so you are essentially minimizing the perimeter of the boundary of the droplet. But you see here I have two terms. So one is the boundary of the droplet, so the boundary of A in omega, which essentially sees the interaction of the set E, so the surface tension given by the set E, the droplet, and I don't know, the gas contained in the container omega. And then I have the measure of the boundary of the set E of the droplet intersected the boundary of omega, because the droplet may somehow sit attached to the boundary and may have some part of the boundary which coincides with the boundary of the set. And you see there is a parameter sigma here, which is called the relative adhesion coefficient, which essentially describes the relative interactions between the droplet and the container, and the droplet and the gas that is contained in the container. And so I will also take a volume constraint. So we'll assume that the Lebesgue measure of the set E is fixed and is M, for instance. One can also add some other functional external forces, for instance, gravity or in general external forces to this perimeter, and things would work as well. But for the sake of simplicity in this talk, I will stick to the case of perimeter-like energy functional. Okay, so what happens when sigma is equal to 1? You see, when sigma is equal to 1, here I have the boundary of E in omega plus the boundary of E on the intersecting the boundary of omega. So if sigma is 1, all in all, I have just the measure of the boundary of E. And so I don't see basically the sigma, the minimizer is essentially a ball, at least for small enough volumes, which I can place wherever in omega. Okay, so I am just minimizing the boundary of E, the perimeter of the boundary of E, and in this case, the minimizer is always a ball, at least for small enough volumes, because it has to be contained in omega, and the ball can be placed wherever in omega. So this is the situation that is called the lotus effect, and the name comes from the flower, that you can visualize here. So it is a situation of completely non-wetting situation, where basically the droplet detaches from the boundary, and you have simply this this ball of water, which may float around, so may be everywhere in the container. The other situation is when sigma is equal to -1, because in this case I have, again, the measure of the boundary of in omega, now minus the measure of E intersected the measure of the boundary of omega. And so you see, if I want to minimize this function, I want to have this part, the second term, as big as possible. And in this case, what happens is that what I obtain, that the minimizer is the complement of the ball, placed wherever in omega the ball, and this is the situation of perfectly wetting, because now I want to maximize this interaction here between the boundary of E and the boundary of omega, so I want this set to be as large as possible. And so the droplet tries to completely adhere to the container of the ball. So this is the other extreme situation where I have perfectly wetting situation. And so we want to consider now the cases, the interesting cases, which are somehow the ones that produce a droplet with some contact with the boundary of the container, like in this situation given by this picture. And so we consider the case sigma between -1 and 1, given that -1 is the completely wetting and 1 is the completely unwetted situation. And so one can actually show mathematically that if I want to have a non-trivial situation, where a non-trivial situation for me means that the droplet somehow attaches to the boundary and I have some kind of contact angle here, like in this picture, then the condition sigma, the absolute value of sigma smaller than 1 is needed. Okay, so for instance, we can check in dimension 2, just for the simplicity of the picture, we can check that the condition sigma smaller than 1 is actually needed if I want to see a non-trivial situation. And so, for instance, I suppose that this one here, the blue one here, is my minimizer. And then what I do, I look for a competitor, and the competitor is this small rectangle here with sides epsilon and delta, with this ball here with radius rho. Okay, so I have to maintain volume, so I want that epsilon times delta, so the volume of this rectangle is equal to pi rho squared, which is the volume on this sphere. And then I use the minimality condition. So I know that that my original picture was a minimizer, And so once I remove essentially the parts that are in common, which is, for instance, this part here, if you see my cursor, so this part here, and then also this part here, which is on the boundary of intersecting the boundary of omega, and this part here, the only things that remain once I do this simplification are, so from the side of the minimizer, I have sigma times delta, which is only this bit here. And then on the side of the competitor, I have what? Well, I have this delta plus 2 epsilon coming from here, and then plus 2 pi rho, which is the perimeter of the sphere, okay? And then I use this expression here to substitute rho, epsilon, and delta. And then I divide by delta and send epsilon to 0, and I obtain that sigma is to be actually smaller than 1. And similarly, one can play the same game if one wants to prove that sigma is bigger than 1. So we will focus on the specific situation in which sigma is in between -1 and 1, knowing that 1 coincides with the lotus effect, and so just minimizers are just balls inside the container, and -1 is the perfectly wetting situation where the minimizer tries to stick completely to the boundary of the container. Another observation that one can do, essentially looking for perturbations which preserve volume and keep this part as it is, one can notice that minimizers inside the container have constant mean curvature, because these perturbations yield that the energy term, this term here, which is the boundary, the measure of the boundary of intersected omega, must be locally stationary with respect to volume Lagrange multipliers, which essentially means that E must have constant mean curvature. Okay, so if I look at perturbations, if I only perturb the part inside here and I fix this part, well, then I see that minimizer must have constant mean curvature. So, and sigma, we don't see sigma in this condition. And so for us, the prototypical setting is that of a droplet, which is a portion of the ball, like in this picture, intersecting the container at some angle. And the contact angle is important. I mean, it has a physical relevance because it is an indication of the wettability of the container. So the flatter the droplet, like in this case, for instance, here, the higher the attraction to the container. So for instance, this case would coincide, for instance, with sigma very close to -1, where you have the very high wettability of the container. And then in this case here, this is very close to sigma equal to 1, where you have the lotus effect. And so the minimizer tries to detach from the boundary. In practice, so because it has a physical relevance, the contact angle nowadays is measured by a contact angle goniometer using high resolution cameras, okay? But the first theoretical determination of this contact angle is actually due to Thomas Young, who has made like really many contributions to the field of mathematics and physics, even the language and also music and Egyptology. For instance, he was also, he took part to the decipherment of the Rosetta Stone, and indeed he's often described as the last man who knew everything because of this eclecticism in his science. So the Young's law can essentially mathematically determine the contact angle, okay, in terms of the relative adhesion coefficient sigma. And in the classical capillarity model, it is cos var theta equal to minus sigma, where var theta, so if you look at this picture, for instance, I'm assuming here that, for instance, the container is flat here, and is given by this dashed line. And so, for instance, this part here would be the droplet attaching to the container. And so this var theta here is the angle that appears in the Young's law. So Young's law, if you know the relative adhesion coefficient sigma, you know the angle. So you can determine the position of your droplet. Now, just for future reference, let me mention that if I call this var theta equal to theta over 2, this angle actually coincides with this here. Just if you just check, you can check this just by trigonometry. So this is just because I will do another computation later on, where this will be involved. So when sigma is positive, notice that when sigma is positive, then you see here the cos theta. So theta has to be in between pi over 2 and pi. And so this means that, so I am in a situation where the droplet tries to detach. So the material is hydrophobic, while when sigma is smaller than 0, then cos theta is positive now. And so theta is between 0 and pi over 2. And so the material tries to attract actually the droplet. And so it's hydrophilic. And so, for instance, you have a situation here that you can see in this picture of hydrophobic, the first case, and hydrophilic materials. And there are many applications, of course. So you want to know the contact angles, you want to understand whether a material is hydrophobic or hydrophilic. For instance, if you want to, for instance, to produce these rushes or these fabrics which are water repellent, you want to, for instance, paints, and there's also this stickiness phenomenon that happens for insects that wants to attach to leaf. So to justify Young's law, we can do it mathematically. We have the same situation as before. So now this dashed line represents the container, which I'm assuming to be flat, and the green part is the droplet. And so now this theta here, this angle here, is essentially twice the angle bar theta. And that's why I wanted to point out before, and this is just trigonometry again. So I want to understand this angle here, essentially. And so the way, well, let's write down the trigonometry. So the length of the circular segment, S, so this bit here, this is theta times r. And then the area of the circular segment, which we denote by A, is explicit in terms of the radius of the ball and the theta. And then the chord, this chord here, is also explicit in terms of r and theta. And so if I assume, I can move this. So if I assume that the area, for instance, is prescribed and equal to 1, then I have an explicit relation between theta and r. So I can write r in terms of theta. And so the energy of the droplet is S. So if I go back, the energy of the droplet is S plus sigma c. This is the perimeter, which I can write explicitly. And then I substitute r and I factor it out. And then I replace theta with the var theta. Now var theta is actually my angle. And now if I take the derivative of this, I obtain this formula here. Now one can notice easily that, okay, of course, this term is not 0. This term is always negative for all theta between 0 and pi. One can simply really check it. And so if I want this to be 0, then sigma plus cos theta has to be 0. So this is exactly Young's law. And so this is a way to obtain Young's law mathematically. Another way is to obtain it is more physical, if you want. So there is a physical explanation. If one just looks at interfacial tensions between, for instance, the solid and the gas, the solid and the liquid and the gas, then you want to have at the contact point here a balance of forces, which tells you essentially that the interfacial tension between the solid and the gas is the interfacial tension between the solid and the liquid. And this bit here comes from the interfacial tension between the liquid and the gas once I project it along this direction. And so cos theta minus cos theta is something which I called sigma, which justifies the name of relative adhesion coefficient for sigma. So it has also a purely physical explanation. Okay, so the problem is, okay, we said in the beginning that this surface tension, this phenomenon comes from, it's the macroscopic outcome of a bunch of microscopic phenomena which involves also long-range interactions between molecules, if you think about, for instance, van der Waals forces and forces like that. So maybe one can try to replace the classical capillarity theory with something that is non-local, where actually our the function, the perimeter-like function we try to minimize actually sees some kind of non-local interaction between points. And this new model has been introduced in 2007 2017 by Francesco Maggi and Enrico Valdinoci. And then we have done some work with Francesco and Enrico, and then also with Alessandra De Luca recently. And I will try to focus more on this last work where we consider actually also possibly different types of interactions between in the two terms of the functional. So this is what we do. We model the formation of droplets in the setting in which we consider long-range interactions. And these remote interactions are modeled on kernels with the polynomial decay. So this is the kernel that I will consider. The basic one is k of x, which is 1 over x to the power n plus s, which I also call k of s of x, just to stress on the dependence on the parameter s. And the parameter s is a number between 0 and 1. Okay, so this is the simplest possible kernel that is polynomially decaying, that is invariant under translations, invariant under rotations, and has nice scaling property. One can consider more general kernels, and we actually do that, and also other people did that. But we can, this is the simplest if you want to take into account these properties. And the point set interactions comes from an original, so the seminal work by Luis Caffarelli, Jean-Michel Roquejoffre, and Ovidiu Sawin, where they introduce this non-local perimeter. And so the idea is that the interaction between two sets, so these joint sets, is nothing but the double integral of this kernel, okay? And then the fractional, the non-local capillarity functional is now this interaction of the droplet with the rest of the container, so with omega minus e, plus the addition coefficient times the interaction of the droplet with whatever is outside omega now. So the first term mimics the molecular interactions of the fluid with the gas inside the container, and the second one with the solid, with whatever is outside the container. And again, as before, one can also include external forces. And we like this interaction because when s goes to 1, the functional recovers up to multiplication by 1 minus s, the classical capillarity energy. So we recover the energy that we just discussed. So there are some conceptual difficulties if one deals with non-local interactions, because of course we have to replace local calculus. So we have to replace computing derivatives with computing integrals, which, as we know, since probably we're at high school, is more difficult than computing derivatives. And so we have to compute integrals and try to detect cancellations, because at the end of the day, we want to average out microscopic interactions which do not impact the macroscopic phenomenon, what we see from far. Cut and paste methods don't work very well because, okay, if I try to move a piece of the set to build another competitor like we did before, well, now they become tricky because, okay, I don't compute perimeters, I have to compute the interaction. So this is trickier than before. We can see more complicated geometry, so not just simple portion of balls, and we can also eventually see new effects that are produced by remote interactions. Okay, so this is just to set the notation. So we look at regular points of E. This is just to have like the main curvature will define at the end of the day, but I don't want to stress too much on this. And we consider the non-local mean curvature of the set at a given point x, which sits on the boundary of E, with respect to the kernel K, which is this object here. Now it's an integral weighted by the same kernel that I have in the perimeter of the characteristic function of the complement of E minus the characteristic function of E. And essentially what I'm saying is that I see, whenever I have points outside the set, I see +1. Whenever I see points in the set, I see -1. And for instance, if I want the mean curvature, for instance, to be equal to 0, well, I want a perfect balance between +1 and -1 in this integral, weighted by the kernel, which is more or less what the classical mean curvature does, right? So if I want mean curvature equal to 0 at some point on the boundary of the set, well, it means that the set must have some kind of balance close by. It's just that here, well, close by must be replaced with everywhere in a Rn weighted by the kernel. So because we are at a regular point, this integral is finite, so we are happy with it. And okay, this is just because whenever k is 1 over x to the power n plus s, we use this short notation. So we don't write k, yes, but we write just s. So there is the Euler-Lagrange equation now, which is not just simply mean curvature equal to a constant inside, but you see you have the fractional mean curvature, but you also have a term which comes from, you see there is a sigma here, which comes from the relative addition coefficient, which now appears in the equation. Notice that this dependence would vanish when s goes to 1 because this term would go to 0. So this is consistent. And then one wants to deal essentially with the same problem. So I want to determine the non-local contact angle. And so to make sense of it, one does a blow up at a regular boundary point. So for instance, if this is my original picture, I take this point x0, and then I do a blow up. So you see now the container becomes the alpha space here H, and E becomes essentially a cone, which is given by H intersected V. Okay, just looking, zooming in very close to x0. And so what is the non-local contact angle? Well, okay, so if I have a critical set for the non-local capillarity theory, or a minimizer more specifically, and if I have the two alpha spaces, which I just described in the picture, so that such as the blow up of omega approaches H and the blow up of E approaches V, so I am exactly in this situation, where if I blow up here, I look at this cone, then the angle between H and V satisfies this identity. Okay, so for every V sitting on the boundary of V intersected H, for every V sitting basically here along this line. Okay, so, and this equation uniquely identifies the angle theta, which now depends on S and sigma between H and V. So you see this here, you have the mean curvature, and here you have a term which involves sigma and involves the kernel. And this is to be equal to 0. So when S goes to 1, this identity is essentially trivial because, well, I'm looking at, so becomes, because this will go to 0, but also mean curvature of the straight line will simply be 0. So this is just trivial. And so if I want to really determine the angle theta S sigma, well, I have to look at somehow higher order cancellations, which use the invariance of the kernel. And we did with Francesco, I will mention Francesco and Enrico, we did the higher order expansion of the kernel. But so just to mention other results in the paper by Francesco and Enrico, also address the interior regularity of the minimizer and the behavior of the bound. So you have nice density estimates and fractional perimeter estimates that hold uniformly up to the boundary. But yeah, this is what I was mentioning. So if I want to make an expansion, a synoptic expansion of the non-local contact angle, and this is what we did with Francesco and Enrico. So when S goes to 1, theta is the arc cos of minus sigma, so we recover the classical case. And then the next term is this object here, this maybe ugly thing here. If instead S goes to 0, the first term in the expansion somehow tells me that the dependence with respect to sigma linearizes, and then I have something in the higher order that one can write explicitly. And so here is the picture. So the term arc cos minus sigma recovers the classical Young's law when S goes to 1. So I recover the blue part here, which is here. But it linearizes when S goes to 0. So it's pi over 2 1 plus sigma. So this line here. Okay, so what we did then when Alessandra De Luca visited Enrico and me in Perth was essentially considering more general kernels, so not necessarily invariant under rotations, and maybe different kernels in the two terms of the interaction. And so the problem is that, of course, it's more difficult now once you have different kernels that are not invariant under rotation. It's more difficult to understand, to detect cancellations. And so one has to be a bit careful with that. So this is the setting. One considers two kernels, K1 and K2, which are essentially comparable to 1 over x to the n plus s kernel, so the classical kernel here. And then one looks at the same interaction, but now with the kernel Kj. And then the energy function is now an interaction between the set, so the droplet and the gas in the container, which is given by kernel K1, and then plus sigma, an interaction I2, which is the interaction of the set of the droplet with whatever is outside omega. And those external forces, same as before, may be taken into account as well. And so this is the Euler-Lagrange equation now. So you see, we have always the mean curvature related to the kernel K1, then you have another term depending on K1, and then you have sigma with another term depending on K2. This is equal to constant. So now the situation is trickier than before. It's not just mean curvatures plus something, is mean curvatures plus two other terms, because now I have two different kernels, so things do not balance out very well. So we have more terms. And then what we do, because again, we want to understand the contact angle, so we try to do the same blow up as before. We want to look at cones, so my set omega, so the container will become the half plane. Once I zoom in very close to the contact point, and the droplet becomes a cone, okay? And then I want also to consider the blow-up limit of the kernels, which is defined in this way. So K star is this limit, you see, R to the power n plus Sj is exactly the scaling of Kj. And so this blow up here is S to B. So we assume that this is some Aj, okay, which now depends, is even, but positive, continuous, but depends on the direction. And then I have the classical kernel, X to the n plus Sj. So it is like the classical kernel, it's just that it's not invariant under rotation. It's anisotropic now, because I have some function that depends also on the direction. And now, of course, as you can imagine, because I have different scalings between the two terms, the determination of the contact angle in this case depends heavily on the different homogeneity powers, S1 and S2 of the kernels. And of course, when sigma is equal to 0, S2, I mean, is free for us to choose because I don't have a second term essentially. So here are the theorems that we prove. So we first assume that S1 is smaller than S2. In this case, this situation happens. So if the coefficient is negative, then the angle theta is always 0. So I have the completely wetting situation. If sigma is positive, then I have theta, where theta is equal to pi, so I have the lotus effect. So essentially what happens is that when S1 is smaller than S2, the second kernel, so the ones that sees the interaction of the droplet with outside the container dominates at small scales. And so we expect it to be determinant for the determination of the contact angle. The kernel K1 essentially becomes ineffective. And so the role of the container now is really pivotal, and the system basically only sees the interaction of the liquid with the solid. And so essentially is the sign of sigma that decides whether the system is completely non-wetting or perfectly wetting. So this is what happens. That is really the second term that matters. If sigma is bigger than 1, then we can say that theta is between 0 and pi. So we don't have the two extremal cases. So theta is like a non-trivial angle, let's say, and is given by this relation here. And if A1 is constant, so I go back to the case of a nice kernel like 1 over x to the n plus s, then theta is pi over 2. Okay, so I have basically the half ball. But in general, it's not obvious. Okay, so I don't see such a simple geometry. I know theta is between 0 and pi, and is given uniquely by this equation. And so notice that here, I don't see sigma anymore, because what happens is exactly the reverse situation. So when sigma is bigger than when S1 is bigger than S2, then the kernel K1 is now the one that dominates at small scales. So I don't see the second term anymore. And so this is the term, so K1, so the interaction between the droplet and the gas inside the container is determinant for the determination of the contact angle. So the kernel K2 is in effect, it happens when sigma is equal to 0. And so the container here becomes marginal, and so the contact angle is fully determined by the interaction of the liquid with the air. So you see only K1. Okay, so this is what you see. So the interesting case is also when, so once you determine what happens when S1 and S2 are different, so you have different scaling for the two terms, so somehow one of the two kernels prevails, and you can say something. So one of the two kernels essentially disappears when you do the blow up. So it's only the other one that force the situation. So the interesting case when S1 is equal to S2, but the two kernels are still different. So they have the same scaling, but they may be different. And so now one expects, of course, that both terms play a role in the determination of the contact angle. One has to assume this condition, which you see tells us that the absolute value of sigma times K2 is to be smaller than 1 minus some small quantity epsilon 0 times K1. And you see when K1 is equal to K2, then I can just simplify K1 and K2. So the condition is exactly the previous one, the one that we had in the beginning, which is sigma is between minus 1 and 1. So sigma between minus 1 and 1 is forced by the physics of the problem, while here, because I have two different kernels, maybe sigma can be somehow maybe larger or smaller depending on the two kernels. And so one can show with the, and it is not completely trivial, one can show that this condition is necessary to ensure a non-trivial contact angle. Though again, in the non-local case, the proof requires a number of finer cut and paste methods. So basically, this is the picture that you have. You consider the container. So, and this is your minimizer. You remove, so you carve out this bit and you add it here. And now, good luck, because now you have to check the interaction between all these pieces here. So the computation with the ball, you remember in the beginning, we carved out a rectangle here and we added just a ball here. That was good enough in the classical case, but it wouldn't work in this case because we would have essentially terms with the same order in the end. And so we wouldn't get any information from them. So one has to do a finer analysis in a sense and add and choose a somehow different and more complicated competitor, but still one can prove it. And this condition is also appropriate because if I want to uniquely identify the contact angle, this is the condition that I want. And so the contact angle theorem in this case, when S1 is equal to S2, is that again, theta, but theta is non-trivial, so it's between 0 and pi, and I have this condition here. So you see here I have three terms, so I see both K1 and K2 star in the blow up. I have the mean curvature here, I have this term, and then I have sigma, the adhesion coefficient, and I have K2. So this is my condition, which uniquely identifies the angle. And the proof, all the proofs essentially in the paper with Alessandro and Enrico rely really on delicate cancellations because now, so you have some kind of anisotropy. So the blow-up kernel is not isotropic. So the cancellations are a bit more delicate than in the case in the isotropic situation, and one has to ask and exploit the fact that the J is even. But still, you see, this is one of the pictures that we have in the paper, and we use this type of cancellations a lot. So you see, you have the half plane. This would be H. This would be this angle here would be my angle, and this cone here would be the blow up of the container. And then you see you have to exploit all possible cancellations to prove that you can have an equation of this type. So this is trickier than in the classical case. And so I think that my time is over. So I will stop here and thank you very much for your attention. And hopefully the audio was fine and you could hear everything.
Thank you. you very much, Professor Serena, for the beautiful talk. We open the floor for questions, comments. So if anyone has some question, please raise your hand or type the question in the chat or open your microphone and ask directly to Professor Serena. So let's wait here some question. Some power, right? What is the intuition behind to this choice?
So this is the kernel, for instance, that you have in the fractional Laplacian.
Yeah,
or in
yes.
the classical, yeah, exactly. In the Gagliardo seminar, when you minimize a non-local energy, that is the kernel. And you can consider more general kernels, but the idea is that you want something that is translation invariant, rotation invariant, that is polynomially decaying, and with a nice scaling property. So this is the idea. And I think Brazil prove that if you take, for instance, S, so you cannot take S larger than 1 or smaller than 0, because otherwise the only functions with finite energy would be constants. So that's why S has to be between 0 and 1. But the idea is that you want something simple, polynomially decaying with nice properties, and you consider that. But you can consider more general kernels, and people have done that also in different settings. Also in the setting of non-local equations, more general integral differential equations. So yeah.
And
the fact is that we also, we also know, we know more results with that kernel, 1 over x to the n plus s, and we want to rely on those results. So that's why we choose the blow up to be like that.
Okay. I have another question, which is, I mean, you have the droplet, and you, which is the liquid, no, and you have a solid, right?
Yeah.
And if you have a liquid and another liquid behind with different density, with like an oil and water, this kind of modelization can be done also.
I think that can change probably the relative Adizio coefficient, because that coefficient, the sigma, that was taking into account
maybe
the relative interactions between basically the substances that you have and that you're taking into account.
Maybe they will depend on x, no? Maybe the coefficient. Maybe the coefficient sigma will depend on x, on the position, no? Because
maybe yeah.
So I have a question, please.
Yes.
So really nice talk, Serena.
Thank you.
So you said that the regularity of the droplet should be C1 alpha with alpha forms S to 1. So we are like to, in the standard case, you need more regularity of the droplets, or so I'd like to say that with this fractional theory, you are like to consider more general droplets in related of the regularity of the boundary.
Yes, so I think that's the right regularity if you want the equation to be satisfied up to the boundary. If you want the mean curvature equation to be finite, or if you want to have all the formulas that I have written involving like these formulas here.
Because of the standard case, you consider a smooth domain. So I mean, you consider that the boundary.
Omega take it the ball, take it smooth.
Okay,
but so for instance, if you want to write something like that, you want to have some regularity. That's why you need some regularity.
So you said that you again C1 alpha.
I think so. I think so. So that's the regularity. Where is the? I think it's. Yeah. Yeah. Alpha bigger than 1. This one here. Yeah, because you want enough regularity to write down the integrals, basically.
So another thing. Okay, it's okay. It's okay. Thank you. So you perform a blow up at the kernels. Why do that exactly? So certainly it's not easy to explain everything, but what's the main intention to make a blow up of the kernels?
Well, this is what you usually do when you.
But the kernel. Huh?
Well, because if you blow up the picture, you're also blowing up. You're also blowing up. You're looking also at the blow up of the kernel.
Okay, I don't figure out, but that's okay. No problem. So nice talk.
Thank you.
But yeah, we had invited the Wojnacki to talk in Bahia from Jean Francisco Rodrigues invited him, myself. He gave a talk exactly in this direction. Enrico gave a lecture in the 200 years from Brazil, the independence of Brazil from Portugal.
Okay.
3 or 4 months ago. Okay. So thank you so much.
Thank you.
Okay, is there any other question or comment? So if not, let us thanks again, Professor Serena. Thank you very much for this very nice talk. So Juan, you can stop